Okay, welcome everyone to the Artificial Intelligence Methods Scientific Working Group for the UCLA-CDU CFAR methods presentation today. I'm Dallas Swendeman. I'm one of the co-leads of the AIM-SWG along with Dr. Kamalata, Jianwei Zheng, our presenter today, and Lola Ongunyemi, also with us today. I'm pleased to introduce Dr. Zheng, who is an adjunct assistant professor in the Department of Preventative and Social Medicine in the College of Medicine at Charles Sturt University. He holds PhD and a master's in business administration. As I mentioned, he's one of our co-leads on the AIM-SWG. Dr. Zheng's work focuses on the application of artificial intelligence to analyze data related to cardiovascular conditions. He has spearheaded studies focused on heart failure, and his research interests include computational physiology, cardiac electronic physiology, cardiac metabolic research, and artificial intelligence, machine learning, and data science. His role as an educator, he supports the cultivation of the next generation of leaders and professionals in the field. And we're excited to have Dr. Zheng present on CardioGPT and ECG interpretation, generation model, and its potential for HIV research.
Well, thank you. Good afternoon, everyone. Thank you for joining us. First of all, let me check. Can everyone see the screen, the presentation slides?
Yeah. Could you put it in slide mode so we're seeing all your slides?
The slide mode?
That's better.
Oh,
Excellent.
awesome. So, awesome. Thank you, Dr. Ogiyami. So, if we have any question for the facility of the presentation, please raise your hand and give us the message. Make sure we have crystal clear communication. Today, I'm going to introduce this real-world case application of the generation AI model to interpret the EKG medical data. At the beginning, I want to make it clear we are not going to create some crossover study between the cardiology and HIV. I just want to introduce this real-world case. How can we use this the modern AI model to address the medical problem? So I don't want to create a kind of confusion to create some ambiguous between the CardioGPT and our HIV study. So today we will go over some of the basic concept about the machine learning and the AI stuff. Make sure we are not be obsessed by this buzzword to over my mind, okay? And then a little bit background introduction for the EKG electrocardiogram data and how this data look like, and the CardioGPT model design results. I will not go over too much deeper the technical detail for the AI model building stuff. We will focus on the general idea and the pipeline. At the last section, we share some the AI potential application using the generative model in the AI HIV research. So the first the AI and machine learning concepts. For some the just entry level the AI the researcher want to conduct the AI related research on the HIV field. So we probably have the conceptual confusion about why we do not use the traditional biostats model. What's the advantage of the machine learning model? Actually, the majority of the mathematical expression for the machine learning model is the same with the statistical model. What's the difference? So the statistical model about the an application layers. The traditional biostatistical model, we want to interpret the statistical association between outcome and the covariates using the samples we collect from the population. we hope we have random samples to present the general situation of the population. That's the application purpose. And for the machine learning model, we have a giant size of the data set. We try to identify pattern or make predictions. We don't put 100% the effort on the interpretation. We care about the accuracy, care about the prediction, care about the application. So the left-hand side, this is the traditional analysis use the logistic regression model. We are going to interpret the factors, the covariate, and effect size, the odds ratio, standard error, the p-value. So to see how from the population level, how do we interpret the association between the covariate and outcome. And the right-hand side is the classical prediction question. So we try to predict these four categories of arrhythmia from the EKG data. We have atrial fibrillation, general supraventricular tachycardia, sinus rhythm, sinus bradycardia rhythm. So we have these four categories. Every sample we have a clear label which rhythm associated with this EKG data, and we build up model try to classify. And the blue color shows the correct prediction, and the off diagonal shows either false positive or the false negative. And we have a matrix to measure the performance of prediction accuracy. And regarding the learning methods, we have two major genres: supervised learning and unsupervised learning. Supervised learning means we know the labels, we know the classification, and we know that the target we are going to learn. And unsupervised learning means we just have a data unlabeled. We don't know how to classify them and how to classify them. So we use the algorithm like the clustering or dimensionality reduction to find the pattern and separate the data into the different group. And after this clustering, we will look at the general pattern and help us to digest the truth, the ground truth of the data. And left-hand side is also a classical supervised learning. We try to predict the origins of ventricular arrhythmia as also cardiac conditions. And we have 19 different locations associated with the intracardiac EKG, and use this electrical graphic data to predict or classify the locations. And on the right-hand side is arterial blood pressure waveform data. That's also graphic data. We try to separate the data for the good quality or the bad quality, generally speaking, using the supervised, semi-supervised, and supervised learning approach. To see finally the clustering algorithm can give us, here this is the group of the signal with good quality, the other group with bad quality, and what kind of anomaly the noise get involved with the bad quality data. And we totally don't know. We have giant size of the data, but never labeled by medical expert or any technicians tell this data is good quality, bad quality, or medium. And the other application, the AI and the machine learning model can do for the different task. We constantly hearing about the classification and the regression, and Dr. Lola Ogiyemi also introduced in our last time seminar. Is if we are going to predict the categorical outcome like disease presents or not, and the risk level. For example, we have four or five levels, and arrhythmia locations. This categorical outcome variable. We try to make prediction. That's the classical classification model can help. The regression model, like this pulmonary artery blood pressure, this continuous variable will show us a continuous waveform. And we have the other covariant variable. Also, they might be either continuous or categorical variable. We can build up a model to predict each data point and finally construct this continuous waveform data and use a regression model with a different loss function. That's much deeper. We will not get through. Just from the application level, what kind of the model we can utilize to help our study. One for categorical outcome, and the other one for the continuous outcome. Okay, let's remove some the buzzword the mysterious abstraction for us to understand the deep learning or machine learning. Actually, these all the machine learning models all developed at least a couple decades ago, and why this AI and machine learning or suddenly get hot, and everyone want to apply these methods to address the challenge. So the one actually three challenges for the overall the AI machine learning application, even for the AI development. In the past, when we're facing the high dimension data, like 3D, like the image data, let's use the example for the grid level image. We have X, Y, and the grid level. This is three dimension array from the data structure perspective. Our traditional model good at the tableize the data, like very structured, like the row presents sample and the column present covariates, right? So there's some the alternative we can use. We can unfold the high dimensional the matrix to be two dimension, but the outcome always we struggle on that. After this convolutional neural network comes up, and then we use this convolution operation to extract actually the edge and the border from the high dimensional data. So this convolutional neural network structure and gradient stochastic optimization, the learning strategy available. We start the new time to utilize the machine learning to interpret, to digest the high dimensional sophisticated time series data from the time. There's not some buzzword or mysterious, just the mathematical, the truth is we just use the matrix operation. No mysterious. Okay. So that means we can, from the other perspective, we can symbolize our data structure and give to the model to learn and to extract the key features from the data. And also, when we deal with the large size of data, there's like the optimization methods, the stochastic gradient descent algorithm make this deep learning available. That's the key component. You can think about that. We have the 2 or 3 terabyte image. No model can load all data into the memory once, and they try to optimize the loss function. But this stochastic gradient descent algorithm, this optimization algorithm, try to use the batch size training, the learning. We one time we just use either 16, 8, or 32 pictures in the one batch training, make this local optimization close to the global optimization. And the new technology, we constantly talking about LLM model, large language model, derived from the recurrent neural network. This network structure try to solve the problem of the time, the sequential data, time series data, like a translation problem. Like I'm talking by Spanish and immediately translate it to the English. That's the sequence data. And the EKG, I'm going to show it later, is also time series data. And attention mechanism, you probably hear that the one popular paper, everything you need is attention. And later on, the transformer structure available, and everyone talking about the GPT, generative pre-trained model, and OpenAI, the Google Gemini. The core concept only based on this formula. Use the softmax function, have this Q key Z Q key V, and I don't want to create a mysterious component here to block us to understand. We can ask a question: what are you talking about this X? What are you talking about this Q key V? Let me tell you, this is simple. This is W key WQ W V, just this X, the input variable itself. And this looks like the simple mathematical operation. We can keep the attention the longer than the previous, like LSTM, the bidirectional as a team structure. Make a large language model can be applied in the real world. So hopefully I didn't bring any the mathematical trouble for us. And the EKG introduction. The EKG is the electrical signal we collect from the human body surface. For the routine standard test, we have 12 lead. Actually, we put 6 or 7 electrodes on the actually, sorry, the 10 electrodes on the human body surface. And we collect this signal like a sine cosine wave combined together. And each heartbeat we can tell from the single heartbeat EKG, like this PQRST. This is a abnormal heartbeat from the normal rhythm. The Q present the atrial chamber physiological activity, and the QRS indicates that the ventricular chamber depolarization of the process. And the T is the recess before the next time the heartbeat. So that's the basic physiology interpretation of the ECG. From the data structure, the science perspective, we can tell this is a multivariate time series data, right? So we have 12 lead is the one dimension, and the time dimension, and voltage amplitude the other dimension. And study design, we have the one side is this 12 EKG waveform data, and the label. We have actually we collect this data from the one hospital in China, and the diagnosis, the original diagnosis is a text data, just a couple sentence. And after from the image data side, first step we need to have data washing, remove the noise, and we learned from the previous study, we either can use the raw EKG data, this 5,000 time 12 the matrices, or we can use the wavelet. Wavelet is a decomposition. We can decompose this the EKG 12 data to a 3D matrices. The wavelet is a mathematical operation to extract the power frequency from the time domain, also aligned with the time domain. That we learned from the previous study might be this feature extraction, and we call the feature engineering methods can help our solution. So after we clean the data, we separated three branches. The first branch we apply the feature engineering methods. And the second branch, we just use the raw EKG data. And so if we have a dimensional data, we are going to use the 3-dimensional GPT model. If we have a 2-dimensional data, we use the 2D GPT model. We just change the size of the input matrix. And it's not a big deal. So. And from the right-hand side, the diagnosis text file, there's the other branch we need to consider. For the in the past, we studied the arrhythmia problem. We interpreted the diagnosis text data and create the classification label like atrial fibrillation, ventricular arrhythmia, atrial arrhythmia, or the blocker issue, like a categorical variable. Actually, our study tried to directly generate the diagnosis sentence, not a classification label. But for the performance measurement perspective, we still want to have a classification label to test the classification ability, prediction ability of the model. So and also feature extraction strategy. So finally, we will have 3 different models to accommodate different structure of the both input covariate and outcome variables. So this data processing, that's the common steps for the electrical image file. Even if we have the other type like echo, MRI, that's almost the same steps to try to remove noise, create the robustness of try to enhance the robustness of the model to accommodate the different quality of the data input. And this is a feature extraction, the wavelet method we are talking about. From the top layer, we have this 2-dimension EKG data. The x-axis presents time, the y-axis presents the voltage. After the wavelet decomposition, continuous wavelet decomposition, on the bottom, these are 4 pages. We can decompose the different level, and each level will represent different power spectrum. So like the QRS complex will shows the yellow close the green color, means the high energy constraint. It's pretty meaningful from physiology perspective. So during the QRS complex, the power released. And we do have some manual checks to see if this continuous wavelet decomposition will give us the more information, not roughly not like the EKG waveform try to interpret this waveform data from the amplitude from the morphology. And the CardioGPT model, we didn't build up this model from scratch. We built up the foundation of the OpenAI's CLIP model. This is the last open source the generative model released by the OpenAI. Right now, if we want to use this generative open source generative model, we need to look for the current available either from the Google Gemini or the other organization. That's not too much challenge for us. Even right now, the OpenAI keep the closed form the business model, and the transformer architecture we introduced before. The that's the core amazing design part of the GPT model. We use the self attention and how to interpret the 3D input variable. We for the yeah, that's a question. If we have a 2D model, if we have a 3D features input, how can we unfold, not simply unfold this 3D array to the 2D. There are some coding technology, embedding and encoding, decoding and encoding strategy we need to use. Make sure that the model can understand the data structure actually we defined, not a mysterious part, just give the raw data. And the diagnosis encoding, that's the same thing we like a translation problem. We build up the dictionary from all the words from the diagnosis sentence data, and tokenize the text words to a token, binary expression. And this slide shows how can we unfold the high dimension data to the 3D dimension. Okay, and from the right hand side, we can tell this is just one picture of the wavelength decomposition, the power spectrum analysis graphic. And if we cut this graphic to the regular square, and each square will be the 3D dimensional input structure, but we kind of unfold this matrix to the flattened expression. We cannot just unfold, directly from right to left to right and from top to down. And we have to give the position information, like the spatial position information and the time domain information, and then we can adapt the transformer structure, give to the model presented on the left hand side. And finally, we have a linear classify layer to generate the text token, and the text decoder will convert the text token back to the natural language. Okay, the general results for our study, we have over 1 million readings from 754,000 patients data, and the mean patient's age is 57.9 years, and 45.9% women. And test data, we have 20% from the total EKG data. And multi-label ECG means the diagnosis have multiple conditions on the one reading. And the ECG classification labels, we totally have 60 classification label, means the 59 conditions, abnormal conditions. And our classification also a multi-label classification. That's under classification. Not it means the multi-label classification means the one sample could have multiple labels, not like a traditional categorical outcome. The one sample only have one label, and the comparison study shows we have the mean F1 score 0.91, the AUC 82. From a classification perspective, we measure this model, and that's the CardioGPT model. Also, we also measure the traditional residual convolutional neural network. The performance below the CardioGPT use the new transformer structure. And from the generation perspective, how to measure the performance of this model, we introduced the two measures, the blue and the red. The blue, like this this matrix is used to evaluate the translation, like we compare word by word for the translation. And RAG try to evaluate the quality of the summary, the overall performance, overall the meaning of the language model. This example, if I give the prediction with the different words or compared with the original diagnostic text file, maybe I bring some the minor program error, or the sequence locations is different. But generally speaking, the meaning still correct. So the RAG can give us this measure the performance. So the blue matrix shows the 2D raw EKG data. The score is below the vividly scaling features, and RAG present the same performance for the different feature engineering strategy. The challenge and the limitation, that's the key component I want to share today. From this study, what's the limitation and challenge? This data collected from the only one hospital. That's certainly the bias. And that's the key question we need to be vigilant to for even for HIV study, for any study, for the machine learning. Yeah, we have the usually optimization we achieve the best variation. We that also means overfitting. We can we use the data trained the model. If we have all data put into the model, we can have almost a 100% accuracy or prediction accuracy, but the variance is it's exaggerated by the overfitting. But when we apply this model trained by the one side and overfitting model to the other side, that's a horrible performance will show up. That's the one point. The second, propose that output utilize both the wavelength scattering and the EKG raw data. The wavelength scattering is good performance, but in the real application, there's a very computational resource constraint. And deep learning model, in the third limitation we need to consider, including the transformer known for the black box nature. If we want to know some nature of the data, we still need to utilize like a causal inference or the traditional biostats test methods to understand the association between the covariate and outcome variable. Okay, here is My suggestions idea how this whatever the GPT or generative large language model, the AI, the modern AI model, potentially can be applied for the HIV research. So the first, what kind of problems the AI can address well compared with a traditional biostats model? We care about the prediction, we care about the application, and we can put interpretability in the manner. And the AI models are good at longitudinal high dimensional data, try to extract the suffixed structure from the high dimensional data, and heterogeneous aging trajectories, and also unlabeled outcomes, and structure and racial disparities. So the AI is not at last, the AI is not intended to replace our traditional methods and study methodology. We should utilize the AI on this challenge problem. We are limited by previous the classical the either biostats model or classical study methods. That's my point. And at least some potential area for the AI can help on the HIV research. The first one is the clinical decision support and interpretation, and treatment adherence prediction, the risk factor stratification, the cohort level pattern explanation. And the second group, precision medicine treatment outcome, ART exposure pattern analysis, the treatment comorbidity interactions, this multi-label classification problem, the high dimension, the image data analysis. And the third group, HIV aging and morbidity trajectory prediction, the AI learning the patterns cross time, like a CardioGPT, not just snapshot. Risk stratification for the longitudinal observation. Identify high risk aging phenotypes, early signals before the clinical events. The last group I can think is a health disparity, the equity focus of the AI. And we can stratify the model evaluation, discovery, the structural patterns, and the bias auditing, not just the prediction. And before we go, I think this slide shows some take-home message. So how potential the CardioGPT structure methods we propose can be applied on the HIV study. This structure can work with the weekly label data, as we know, the more challenge the medical problem, we more likely we not have the clearly labeled data. So the more ambiguity in the challenge area, right? So the CardioGPT structure can use this weekly labeled data, like just summary of diagnostics and summary of the medical notes, and we can accommodate the multimodal data. Like we can use the image data, we can use time series data, we can use the even the structural the EHR data. Just need to change the network structure to inject this categorical variable or continuous variable in the different layer of the neural net structure. And that's the advantage of our GPT structure. And and what we should be careful. The AI is not a causal inference, and the AI is not clinical decision, replacement, and it's not naturally bias free. We have to cautiously examine the bias. And the final slides, I introduce some knowledge from the AI field, and from the two angles, the AI science or data science researcher, we should know from the bottom to the top. But from clinical researcher like us, the HIV researcher, we definitely we need if we can know all the knowledge, that's the best. But from the practical perspective, we can understand the clinical application, and we can interpret the bias and the fairness check, and we know how to do the validation, the usage adaptation, and go to the deeper. We don't need to know too much mathematical foundations. Build up the model from scratch, design structure. That's the AI data science researcher. Should naturally should handle these type of jobs. So from our perspective, we need to know, after we have the AI machine learning model ready, after training, we should know if this model will be biased, and how to interpret the result. And we still need to keep in mind the causal inference and even the association interpretation. We still need to put the time to consider. The AI cannot address everything, especially for our researchers. Okay, this work, we would like to thank Dr. Dr. Annie Abdai, and Dr. Rikoski, and Dr. Chu and Fu, and Asan, my colleagues, and the Louis from Children's Hospital of Orange County. We work together. You can tell from this group structure. We have data science AI researcher, we have biostats, mathematicians, and cardiologists. So we work together to finally come out with a solution to tackle this problem. And the other acknowledgement, this work is supported by Axis, the Axis grant, and the UCLA-CDU for this AS1 group 2, and also I'm supported by this Caesar Cancer Award for innovations in HIV prevention and care. And to these examples, we used all the our group previous AI machine learning work. Now we have some time for questions. I hope I didn't scare us by so many the AI machine learning model structure introductions.
No, thank you, Dr. Zheng. Let's see. I think I saw a slide on future directions. Maybe you skipped for time, and we can come back to that if we don't have questions. Um, one of the
I did
questions
have
I
a
always have is you'd mentioned. Oh, Lola, go ahead.
no, you can go ahead. That's okay.
Well, it's a kind of a bigger picture question, but one of the limitations you mentioned was sort of the black box factors, right? So what are ideas or what are some solutions? I've heard of things called explainable models.
Mhm.
So how might that work in your example?
Oh yeah, that's a very good question. So that's also my future work. After we have this whatever the AI machine learning model done, right? Very good performance on prediction or the or classification. So we are curious these important features as the real causal connection with the outcome, right? So we have a we have to have the continuous like different sampling methods and different sampling strategies and either apply the traditional bias that means we can shrink the data set size can be accommodated by traditional bias model or causal inference and analysis, the methods. And then we can further to test is this association or causal, right? Did I answer your question?
I think so. To paraphrase, you would replicate the analyses with traditional biostatistical analyses models that would provide stronger causal inference results.
Right. So we can test
Mhm.
either if this prediction works well by the association or by the causality.
Great. Thank you.
Yeah. And that's the other key aspect we can consider. For right now, I didn't see too much study to go further. After machine learning model is done, or the perfect prediction, that's it. So no further analysis. Actually, after this prediction work is done, we can pick up the important feature. Let's see and we can shrink the size of the data set. That's the traditional analysis model or the methods we cannot handle because we have the image data, we have the multivariate time series data, right? So after we can have condense these key features, we can do further analysis to have a more robust in the test.
So extending into a hypothesis testing framework.
Right, exactly. So I didn't see too much research on this direction. I think that's we should do that to from the academic research perspective, right?
Great. Thank you.
Mm. Douglas, okay, I mean, do you have any questions?
Yeah, so this is a more practical, a narrower question. So if you were going to use CardioGPT in a new setting, right,
Mm.
where the sort of ECG diagnoses are in structured form, do you have to convert those to labels, to text labels, essentially, in order
Oh,
to, yeah.
yes, that's a really good question. Actually, we have this meaning, the meaning readings. It's not reliable. We hire so many physicians to translate the text file data to the classification label. We also use the GPT model. After this always this diagnosis text file repeat pattern. We just keep out the keywords and ask physician cardiologists to pick up the combination. And after we have this combination reference, we have this text file. We apply additionally from the open and the GPT model to summarize the text file to the classification label. Yeah, that's a very tricky part. We cannot hire over hundreds of physicians to relabel it again. It's kind of tricky.
Any questions from our other participants? Okay, well, thank you so much, Dr. Zheng, for a presentation. I really appreciated how you presented in a way that kind of took a deep dive into some of the the mathematics and the quantitative data science elements, but then also it kind of broadened out into the big picture issues and addressed how we might apply these methods in HIV related aspects. Um, to everyone in the room and online, we'll be sending out an evaluation form. I think there will be through a Zoom follow-up or link, and it might even be provided at the closure of the Zoom meeting. So please complete the evaluation. I think we might have a form or field to let us know if there's other topics you're specifically interested in. Um, and thank you again for your participation, and we look forward to seeing you in the next month or so for another presentation or workshop. Thank you again, Dr. Cheng.
Thank you. Thank you, everyone.